guys, nice to see you. Let us recall first last question. We introduced heat engine and heat pumps. What is the difference between heat engine and heat pump? Mhm. So what is heat engine? Let's start from that. We have some hot reservoir, then heat engine absorbs heat from hot reservoir. Part of this heat is used for performing work on external environment, and other part will be expelled to cold reservoir. So that is natural process when heat is transferred from cold to cold, from hot to cold. However, if we want to reverse this direction, that is already heat pump. When we want to take heat from cold reservoir and transfer it to hot reservoir, what is the requirement for that? Need to perform some external work on the system. So otherwise it doesn't go like this. A natural process. So in the scope of this definition of heat engine, it's possible to formulate the second law of thermodynamics. And who will help me to formulate it?
It is impossible to create a heat engine that does not dissipate any heat into the environment.
Like cold reservoir, whatever we understand under this. So means, in other words, it is impossible to have the only outcome of heat engine, which in the form of some work, when we convert all heat absorbed from cold reservoir into work. So part of this energy should be expelled to cold reservoir. So when we deal with heat pumps, we need to specify how we use this heat pump. Either we cool cold reservoir or we heat up hot reservoir, because depending on the conditions of application, we need to calculate the COP, coefficient of performance, differently. When we care how efficiently we cool down the cold reservoir, we obviously consider QC, cold reservoir heat, which we absorb from cold reservoir. And then if we want to determine how much we heated the hot reservoir, we consider QH in the numerator, and in the denominator is work done on the heat pump in order to make this process happen. Otherwise, it doesn't work. So we also considered in details this general operation of a heat pump based on regular freon-based refrigerator. And there are two key moments which need to be considered in this system. First of all, unique properties of freon. So what can you tell about unique properties of freon as a working medium with this heat pump?
Its temperature is highly dependent on pressure.
Opposite, boiling pressure is strongly dependent on temperature, and that is the key requirement, because otherwise we will not be able to realize this technically. So we clearly define two regions in the refrigerator where we have low pressure and high pressure. And what is the driving force for this work done on the system in order to make the heat pump working? the compressor. That is the mechanism which performs work, and that's the mechanism which allows us to make this transition from low to high pressure regions, which significantly changes boiling temperature, and as a result, we eventually can realize this closed cycle. So today we continue with heat engines, our discussion, and that will happen with the introduction of so-called Carnot engine or Carnot or heat engine which is operating according to Carnot cycle. So this is some hypothetical uh, heat engine with performance higher than any possible real heat engines. So it will be the highest performing heat engine. And the reason for that, it is operating according to reversible process, and there will be no lost energy. So all other real heat engines, they will operate with not reversible processes, and unfortunately, because of additional energy losses during the operation, we will lose energy and performance will be low. So there are so-called two Carnot theorems, and first one tells us that efficiency of Carnot engine does not depend on working medium, doesn't matter what is it. And what is the most important, that this performance depends only on temperature of cold and hot reservoirs. Um, so that is the first Carnot theorem, and the second tells us that it cannot operate, that we cannot design any heat engine which operates with higher performance than Carnot engine. So let us first start to consider second one in a very simple approach, to show that indeed it should not be possible to have any engine with higher performance than Carnot engine. And then we will come to the first one where we need to derive the expression for performance of Carnot engine. So let us consider some closed system. Hot reservoir, cold reservoir, and we have two engines. So this will be regular heat engine, and this will be Carnot, but working in heat pump mode. So we still call it Carnot engine, but with arrows we will show what they actually are doing. So heat engine is operating in normal regime. So it absorbs some heat from hot reservoir, performs some work, and expels the rest of heat to cold reservoir. But this work is performed not for nothing, but for running the Carnot engine as a heat pump. So we know that in order to operate as a heat pump, we need to perform some work. So in this case, what will happen? Carnot engine will work as a heat pump, will get some heat from cold reservoir and expel it to hot reservoir. And now we assume that efficiency of this heat engine is higher than efficiency of Carnot engine. So what that will tell us? If that is true, this assumption, then work which is performed by heat engine will be enough to run the Carnot engine as a heat pump. Means that, well, they have the same hot and cold reservoirs, the same temperatures, everything the same. Means that this system being isolated from external environment will continue working. But that is violation of second law of thermodynamics, which states that it is possible to run heat pump only in that case when external forces perform work on the system. So this system cannot operate, and that means that this situation when we have um, larger or even equal efficiency of heat engine than efficiency of Carnot engine is not physically valid. So that's such a thinking experiment which just highlights this um, fact that Carnot engine should possess the highest possible performance. And now we need to consider step by step each of the thermodynamic process which forms the Carnot cycle, because that is the basic uh, concept of Carnot engine. So for that we have this pressure versus volume plot and consider for thermodynamic processes. So for convenience we show two isothermal processes, two isothermal curves. Each of these curves corresponds to some constant temperature, so TH and TC, temperature of hot and cold reservoir. So what then we consider? Before we go into each step, let us also consider a system which we operate as a Carnot engine. So in this case, we will deal with ideal gas, and that will be a cylinder with a piston. So here we have ideal gas. Then we assume that this piston walls and cylinder walls, besides the base part, they are thermally insulated, means heat cannot transfer through these walls. Then there are two options for the base part. It's either some thermal insulator, which blocks, if we place it here underneath the cylinder, it will block completely any heat transfer from ideal gas to external environment and in opposite direction. Or we have cold or hot reservoir. So we can replace either thermal insulator, cold or hot reservoir, depending on the steps of Carnot cycle. So now let us consider first step. So let's be point A, it's our starting point. So this will be point B, and we have first thermodynamic process in Carnot cycle. So that is process A, B. So what process is this? So that is isothermal curve. And both points, A and B, are located at the same isothermal curve. Means obviously that is a isothermal process. And what we can say in terms of temperature between these 2 points? It's the same, it doesn't change. So we can write the temperature is TH, so for this process, TH, oops, not H, and that is constant. Also, what we can see here, that volume, if we go from point A to B, volume is increasing. So it means that this piston is moving upwards, and that means that gas is performing work on external environment. So this case, there is some work, AB, which is done by the gas on external environment because gas is expanding. And obviously this process happens when we place here underneath of the cylinder some hot reservoir, which will provide QH amount of heat into the system. So what is the source of this work done by the system? Because volume is increasing. That is the amount of heat which is absorbed from hot reservoir. Since internal energy remains constant, temperature doesn't change. So in this case, we consume heat from hot reservoir and perform via this isothermal process. Now let us consider second process, and that is process BC, will be BC, which happens when we, instead of hot reservoir, place here a thermal insulator. So we completely thermally insulate our ideal gas, and taking this factor into account, what process BC would be? Adiabatic process, because there is no heat exchange with the external environment between the interface of the system and environment. So we isolate. This is a adiabatic process, and what we see from the volume, it also increases. Volume further increases. So we have now temperature change from TH to which temperature? TC, because we move from one isothermal curve to another. And because of this, we don't have any external source of heat now because of reduction in internal energy. This gas performs work by increasing volume and moving this piston further up. So that's why we have also work done by the system during process BC. So now we consider the third process, which is CD, as second isothermal process in Carnot cycle. And during CD isothermal process, we place already cold reservoir in contact with the bottom of the cylinder. And during this process, some amount of heat QC is expelled to cold reservoir. So now, what is important here, first of all, temperature doesn't change because we already cooled down the initial temperature reduced to from TH to TC. And now we reduce volume. We move this piston down, so it means we exert some external force which performs work on the system. Since internal energy is not changing because temperature remains constant, this work done on the system transforms into heat which is expelled to the cold reservoir. So here we can write that temperature is constant And now already external force performs work on the system, so means we can, just to highlight this, we can write minus here. Minus some work done during process CD. And that means that the piston is moving downwards. So now we come to the point when the last step of the process of Carnot cycle is performed, and that is another second adiabatic process. When we place again here this insulator to have fully thermally insulated ideal gas, and volume further decreases, so piston further moves down. That is process DA. So in this case, what happens? We insulated ideal gas, and there is still some work done on the system. That results in the increase of internal energy because heat cannot be transferred anywhere. So that's why we have temperature change from Tc to Th. And also there is some work, dA, done on the system from external force. So that is step-by-step discussion of all thermodynamic processes, two isothermal processes, two adiabatic. During isothermal processes, we either get heat from hot reservoir or expel it to cold reservoir, depending on the process. So now let us consider how we can determine its performance. So performance of a heat Carnot, well, any heat engine can be defined, we discussed this previously, as unity minus QC over QH. So that is general definition of performance. Now we want to determine how we can replace this ratio with temperature of cold and hot reservoir, because what first Carnot theorem tells us that performance of Carnot cycle is determined only by temperature of cold and hot reservoir. So for that we need to consider all steps, and we need to recall here that few lectures before we derived an equation which gives us the work done on the system from side external environment during isothermal process. So that was nu, amount of moles, times R, universal constant, times temperature T, times natural logarithm V initial over V final. So that was, according to our derivation, work done by external forces. That's important. So now let us consider first isothermal process, which is AB. Work done during this isothermal process is done by the system on external environment. So we kind of flip it over. And of course, initially we can highlight that change of internal energy in general, according to first law of thermodynamics, will be equal to Q plus W, and then we can write that absolute value of heat will be equal to work done by the system during isothermal process, because this is equal to 0 for isothermal process. So we can write that during this isothermal process AB, QH will be equal to work, because there is no change of internal energy. So we can write further, this will be equal to nu times R times T. Temperature is TH during process AB. And here will be natural logarithm of V initial over V final. That's for work done by external force on the system. And now system is performing work on external environment. So we can just flip them over because we can use minus to specify that. So V final in this case will be VB, and here initial is VA. So that is for process AB. And we still have another isothermal process, which is CD. So CD, in this case, we can write that QC is equal to work. Now work done by external force on the system because piston was moving downwards. In this case, we just use this equation as it is. So it will be nu times R. So now temperature is Tc times natural logarithm of Vc over Vd. Should be like this. And we look here on this expression for efficiency of Carnot cycle. We have this ratio Qc over Qh. We can write that Qc over Qh will be equal to the ratio between this equation and this equation. So it will be nu times R Tc times natural logarithm Vc over Vd divided by nu times R Th natural logarithm Vb over Va. So these guys can be cancelled out, and eventually we have Tc over Th. That's already what we want to have, this ratio with temperatures, but we still have another term, which is natural logarithm of Vc over Vd divided by natural logarithm of Vb over Va. So that is what we getting from analysis of two isothermal processes. Now we still have two adiabatic processes, which are BC and DA. So BC and DA. For adiabatic processes, we can write relationship between volume and temperature, which we mentioned during our previous discussions. So we can write that TH times VB in power gamma minus 1. Remind me, what is gamma? Coefficient, and what is equal to? So gamma is equal to ratio Cp over Cv. And Cp and Cv stand for specific molar heat capacitance at constant pressure and constant volume respectively. So for the process dA, we can write Th times Va gamma minus 1 is equal to Tc Vd gamma minus 1. So now what we do, we divide the first equation by second equation. So that you see Th here, Tc and Tc, they will cancel out. So we will get from that Vb over Va in power gamma minus 1 is equal to Vc over Vd in the power gamma minus 1. So what it tells us, since powers are the same, so their arguments should be also the same. So means Vb over Va is equal to Vc over Vd. And from here, we can write that natural logarithm of Vc over Vd is equal to natural logarithm of Vb over Va. Now, let us again write down this ratio Qc over Qh. That will be Tc over Th times ratio of this natural logarithm Vc over Vd divided by natural logarithm Vb over Va. And this ratio will be equal to unity, since this numerator and denominator are the same. So eventually it will be Tc over Th. And based on this, we can write that efficiency of Carnot cycle will be unity minus Tc over Th. That is the equation for Carnot cycle efficiency as heat engine. And indeed, according to this first Carnot theorem, only two parameters, temperature of cold and hot reservoir, define the performance of Carnot cycle. So looking at this equation, what suggestions are in order to increase the efficiency of Carnot cycle? Okay, so you go for extreme case on efficiency unit. So that's true. If we keep the cold reservoir at 0 temperature, then we don't have this part, we have unity, which theoretically possible, but actually to reach 0 it's even theoretically not possible, but very close to 0 possible, up to some millikelvins. However, that is not very practical case, because that's extremely difficult to achieve. Most reasonable when we consider cold reservoir as our environment, which, let's say, room temperature, 25 degrees Celsius, and that is kind of more or less fixed. Then the other option is to increase temperature of hot reservoir. So we want to get it as high as possible. By the way, there is even an option, sometimes people estimate maximum performance of solar cells, those devices, semiconductor devices which convert light into electricity, in the scope of Carnot cycle. So they consider cold reservoir temperature as environment. And what do you think they consider for high temperature reservoir in this particular case? Sun, the temperature of the surface of the sun, which is plus minus considered to be something about from 5,500 and up to 6,000 degrees Celsius. Quite an high temperature, which definitely you wouldn't be able to realize here on Earth. But if you're not talking about some thermonuclear artificial thermonuclear So, but it's very rough approximation. Obviously, there are much more detailed calculation of theoretical performance of solar cells based on quite a shorter limit detailed balance. But this sometimes is used. So even for such extreme cases, people are applying this simple equation in order to estimate the highest possible performance. And another thing which is highlighting the first theorem, Carnot theorem, that the working medium doesn't matter, like working element doesn't matter for performance. So we consider here, derive this equation for ideal gas, but it can be applicable in some extent even to estimate performance of solar cells which do not have anything related to ideal. So we also can utilize Carnot engine in the reverse as a heat pump, and that will be also the most efficient heat pump possible in theory possible, because we cannot realize so efficient processes, but it's theoretically most efficient process, this Carnot cycle. So if we want to operate as a heat pump, then we have this COP, which stands for coefficient of performance, for, let's say, cooling. Then how we define COP for cooling? Remind me. Huh? Amount of heat which we took from the cold reservoir divided by work which we used to realize this process. So QC over work. Then how do we define work? As the difference between QH and QC. So taking this into account, we can write that it will be 1 over unity minus QC over QH. And we already have shown that this ratio for Carnot cycle will be Tc over Th. So we can write 1 minus Tc over Th. And in other form, we can represent it as Th over Th, oops, minus Tc.